All right, so the last topic we want to talk about in functions is inverse functions. But first, we have to talk about inverse relations. So given a relation R from A to B, remember, we have relations from A to B. If you don't remember what this is, go back to the last video on relations, section 16.6. And there's a short video about relations from A to B. So given a relation from A to B, the inverse relation of R, the inverse relation, which we denote like this, is a relation from B to A. So you can pronounce this as R inverse, or the inverse of R. So it's a relation from B to A, so it's going backwards, defined as follows. R inverse is the set of all ordered pairs y comma x, such that the ordered pair x comma y is an element of the relation R. So in other words, it contains the same pairs as R, but flipped around. Each pair is flipped around. So again, you take all the, what's R? R is a set of ordered pairs. You take all those ordered pairs, flip them around, flip each of them around, and that gives you the set of ordered pairs that is R inverse. So for example, let's say we have these two sets A and B, and suppose we have the following relation from A to B. We'll call it F. We'll say F equals this set of ordered pairs. This is a relation from A to B. Remember, it's a subset of A cross B, meaning each pair here has an element coming from the first item in each pair comes from set A. The second item in each pair, like this too, comes from set B. And that's true for all these pairs. So F is a relation from A to B. All right, now what is the inverse relation? So F inverse is the following relation, not from A to B, but now it's from B to A. And here it is. F inverse is the following set of ordered pairs. So notice it's the same pairs as in the original set, but each pair is flipped around. Here's a picture view of what's going on here. So here on the left, we have F, okay, the original relation. So we have A comma 2, B comma 3, C comma 1. Now on the right here, or rather in the middle, we have the inverse relation. So we have F inverse. Okay, so notice the arrows are the same, but they're pointing the other way. So 1 comma C, 2 comma A, 3 comma B. Let's do another. Notice that both F and F inverse in this example are functions. Now that's not always going to be the case, but in this particular example, F is a function, right? And F inverse is also a function. Let's look at another example, same sets A and B. Now let's have a different relation, which we'll call G. It's a relation from A to B. It has these ordered pairs. And so what is the inverse of G? So G inverse is the following relation from B to A. So it's the same pairs, but each of them is flipped around. So here's the picture view. So on the left here, you see the original function, the original relation G. And in the middle here, we see G inverse, which is the inverse relation. Now, G is a function. Okay, this thing on the left, G is a function. Why? Because for each element of A, there is exactly one ordered pair starting with that element. So we have A comma something, B comma something, C comma something, and we don't have any duplicates, right? We don't have two pairs starting with B, or two pairs starting with C, or two pairs starting with A. So G is a function. It's a special type of relation, but it's a function. Is G inverse a function? Okay, no. And you can see that from the picture, or you can see it from the ordered pairs. We see here that we have 3 comma B and 3 comma C. So this is not a function. So notice that G is a function, but G inverse is not. So what we want to know is, if I have a relation from A to B, and I find the inverse of that relation, when is that inverse going to be a function, and when is the inverse not going to be a function? So we have the following theorem. Let a function, let's say we have a function from A to B. Remember, a function is a special type of relation. So we're really talking about a relation from A to B, but a special type of relation, which is a function. So let's say we have a function f from A to B. Then f inverse, so that's the inverse relation. F inverse is going to be a function if and only if f is bijective. So in other words, how do we know if the inverse of a how do we know if the inverse of a function is going to be a function? The answer is, it all depends on whether the function is bijective. So if f is bijective, we have a function that's bijective, then when we find the inverse, that is also going to be a function. So going back to the most recent example, the original function g is not a bijective function. It is a function, but it's not bijective because in particular, it's not injective. Right? So we have two things that go to 3, right? B and C both go to 3. So it's a function, but it's not bijective. And therefore, the inverse of g, which is here in the middle, the inverse of g is not a function at all. And going to the earlier example, so function f here on the left is a bijective function. It's bijective, and therefore the inverse of f is also a function. Okay, so again, if we have a function, whatever it is, from A to B, then the inverse is a function if and only if f is bijective. All right, so now we can define the idea of an inverse function. An inverse function is really just an inverse relation, but it has to be a function. So if we have a function f from A to B that is bijective, then its inverse is the function f inverse from B to A. Right, so it's really the inverse relation, but since in this case f is bijective, therefore the inverse is also a function. Okay, so this is the inverse function. Now let's talk a little bit more about what an inverse means. The inverse of f undoes whatever f does, right? So f has a certain rule that for certain inputs, you get certain outputs. For input A, you get output Z. For input B, you get output Y, whatever, right? So the inverse of that, the inverse function undoes that, right? So given an output, it tells you what the input would be for that. That is, f inverse is the inverse of f if and only if f inverse of f of x is equal to x for every x in the domain of f. So what does this mean? This is a formal way of saying that the inverse of a function undoes what the function does. So here we have a function f, and we're saying that if we give it an input of x, so we do f of x, so we apply the function, and then we take that and apply the inverse to that result, so we do f inverse of f of x, we should get x, meaning f of x does something to x. Sorry, f does something to x, and then we take that result and give it into f inverse, and we get back the original thing. So f inverse undoes whatever f does. And this is supposed to work for every x in the domain of f, right? So if we have that this is true for every x in the domain of f, then we know that f inverse is in fact the inverse of f, right? In other words, we know that if we have something like this, it's in fact going to be the inverse of f, assuming that this equation works for every x in the domain of f. All right, let's look at some examples of functions and inverses. So consider the function f from the set of natural numbers to the set of positive even integers. Okay, this is a set of all positive even integers, 2, 4, 6, 8, ... And let's say the function is defined by f of n equals 2n. All right, so the inputs of the function are any natural number, and the outputs are just going to be even numbers. Now, that makes sense because 2 times n means you take whatever you're given as input and you multiply it by 2, so the result is going to have to be even. So here, that's our function f. Now, I'm going to show you that f is a bijective function, and I will show you this by showing you that it is injective and surjective. And remember that when a function is injective and surjective, it is automatically bijective. So let's show you, let's see whether the function is injective and surjective. So the function is injective for the following reason. Remember, go back, if you don't remember go back and see how we prove that a function is injective. So what we're going to do is we start off by saying, let's say f of n is equal to f of m. So suppose we have, suppose we know that f of n is equal to f of m. Well, what does that mean? Well, that means 2n is equal to 2m, just plugging in the values into the function. And then we can simplify this. So this means that n is equal to m. All right, so this line here proves that the function is injective because it shows us that if we have f of n equals f of m, that must mean that n is equal to m. And that, remember, this is the contrapositive approach. If you go back to that, to section 16.2, this is proving that function f is injective. How about surjective? So for surjective, we have to make sure that for every little b, or whatever, for every b in the domain, sorry, for every b in the codomain, and this is the codomain here. So for every b in the codomain, we need to make sure that we can reach that b, right? How do we prove that a function is surjective? We show that every element of the codomain can be reached by the function. So for every b in the codomain, so first of all, we note that if we do b divided by 2, that's a natural number, right? If you take any even number, like 2, and divide it by 2, it's a natural number. If you take 4 divided by 2, it's a natural number. If you take 6 divided by 2, it's a natural number, and so on, right? So you take any even natural number, and you divide it by 2, you get a natural number. And f of b over 2, well, that's going to be 2 times b over 2, which is b. So what did we show just now? We just showed on this line that for every possible output, for every element of the codomain, right? For every element of the codomain, it is possible to reach it, right? So if I have an element b in the codomain and I want the function to reach that element, well, I'll just do f of b over 2, and that will give me b. So that will allow me to reach b. So the function is surjective. All right, so we see that the function is injective and surjective, so therefore it is bijective. Now, I just want to stop here for a second, because if you really are thinking about this, it should seem rather strange, because a bijective function matches up the elements of the domain and the codomain, right? And they match up like your right, the fingers on your right hand match up with the fingers on your left hand, right? They just match up. So so it would seem, well, and in fact it is true, that the size of these two sets, right? The size of the domain and the size of the codomain should have to be the same size, right? If a function is bijective, that should mean that the domain and the codomain have the same size. And that is in fact true. But notice what we're saying here. We're saying that the set of natural numbers, which includes odd and even numbers, has the same size as this set, which only includes positive even numbers. It would seem like this set should be half the size of the natural numbers. But actually, mathematically, they actually have the same size. We're not going to get into this at all, but there is a chapter on this topic in the book, chapter 18, I believe. It's called, well, it's all about infinite sets. What's really going on here is that when you have infinite sets, things aren't so intuitive as they are with regular sets, with finite sets. Anyways, let's move on. So we have this. We see that f is bijective. So since f is bijective, f must have an inverse function from the set of even positive numbers to the set of natural numbers, and it is defined by f inverse of n equals n over 2. All right. So in other words, we need to have something that undoes whatever f does. So if f takes the input and multiplies it by 2, then the inverse of f will take the input and divide it by 2, because multiplication and division are opposite operations. Now, let's verify that this function that we found here, or this function that I gave you here, is truly the inverse of f. Right? So how do we verify this? Well, we use what we said here in the definition, that f inverse is the inverse of f, if and only if f inverse of f of x is equal to x for every x in the domain. So what we want to know is it true that f inverse of f of x is equal to x? So let's verify that. So we note that for every n in the set of natural numbers, right? So that's the domain of f. What is f inverse of f of n? Well, that's f inverse of 2 times n, right? That's f of n. So that is, well, f inverse says you take the input and divide it by 2. So that's 2n divided by 2, which is just n. So notice, for every n in the domain, f inverse of f of n is just equal to n. All right, so this shows us that we really truly found the inverse of f. Now let's talk about logarithms. And it might seem at first glance to be totally unrelated to anything we're doing here, but we'll see that it's very closely related. In fact, logarithms are a type of inverse function. So let's recall some facts about logarithms, which we haven't seen yet. We haven't covered this semester, but you've certainly covered in earlier courses if you're taking this course. So what does it mean? What does log base a of x mean? Or what is the result of that going to be? So log base a of x is the number y for which a to the power of y is equal to x. In other words, when I say log base a of x, what I'm saying is what power do I have to raise a to in order to get x? Meaning a to the power of what is equal to x. So what I want to know is y. A to the power of what is equal to x. Well, so I want to find y. That's exactly what log base a of x means. And there are many formulas about logarithms, which you have learned about in an earlier course, but here are 2 of them, which we'll use shortly. So one of them says the following: log base a of a to the power of x is equal to x. So this is pretty reasonable, because what does this say? Well, this says if I start with a, what do I have to raise a to the power of in order to get a to the power of x? Well, it's pretty obvious. If I start with a and I want to get a to the power of x, I just have to raise a to the power of x. So the answer is x. Another formula: a to the power of log base a of x is equal to x. All right, so let's now look at an example involving inverse functions. So consider the bijective function f from the set of real numbers to the interval of real numbers starting right after 0 going to infinity, defined by f of x is equal to 2 to the power of x. All right, now let's prove that f is bijective. So f is bijective since it is both injective and surjective. Let's show that. So how do we know f is injective? So if f of x is equal to f of y, that means that 2 to the power of x is equal to 2 to the power of y. Now, how do we simplify this? Well, what we do is we take the log of base 2 of both sides. So again, log base 2 of both sides. So log base 2 of 2 to the power of x is equal to log base 2 of 2 to the power of y. But what is log base 2 of 2 to the power of x? Well, from this formula, it's going to be just x. And then what is log base 2 of 2 to the power of y? Well, it's just going to be y. So therefore, x is equal to y. So we showed that if f of x is equal to f of y, then x must equal y. So therefore, f is injective. Let's show that f is surjective. So for every b in the codomain of f, we have that log base 2 of b is a real number, so it's an element of the domain, and f of log base 2 of b In other words, if we take log base 2 of b and send it as the input to f, that is going to be 2 to the power of log base 2 of b, right? Because f of x says 2 to the power of x. So f of log base 2 of b is going to be 2 to the power of log base 2 of b, which is equal to b. So we showed that given any b in the codomain, there is a way to give an input to the function that produces b as the output. So therefore, the function is surjective. Now, since f is bijective, it has an inverse function. And the inverse function goes from the interval of real numbers starting right after 0 going to infinity to the set of real numbers. And it is defined by f inverse of x is equal to log base 2 of x. That's the inverse function of f. Let's verify that this is in fact the inverse. To verify that f inverse is truly the inverse of f. So let's just pause here for a second. Notice exponential function and logarithmic function are inverses of each other. So if I have an exponential function, whatever, a to the power of x, here it's 2 to the power of x, then log base a of x is the inverse of that. Right? This is just a particular example where we have 2, but in fact, it's true more generally. Right? If I have a function a to the power of x, that's an exponential function. The inverse of that function will be log base a of x, logarithmic function. Okay, let's verify that f inverse, that this thing that we found here is truly the inverse of f. So let's do the following. For every x in the set of real numbers, let's try to find what is f inverse of f of x. So f inverse of f of x. So f of x is 2 to the power of x. So this is f inverse of 2 to the power of x, which is, hold on, sorry, that was a typo, right? So, okay, so this is f inverse of 2 to the power of x, which is log base 2 of 2 to the power of x, right? Because that's f inverse. Log base 2 of 2 to the power of x is just x. So in other words, for every x in the domain, f inverse of f of x is in fact equal to x. So that shows us that what we have found is really the inverse of f. Now, how do we find the inverse of a function in general? So there's a procedure. So to find the inverse of a function f, there are 3 steps. First of all, write it as an equation. Write the function as an equation. Y equals whatever the function formula is. Then interchange x and y in the equation. And finally, solve this equation for y. So let's look at an example. So consider the bijective function f from the real numbers to the real numbers, defined by f of x is equal to x cubed plus 1. Okay, so now we're not going to bother proving that this is a bijective function. I'm just telling you it's a bijective function. We would like to find the inverse of this function. So to find the inverse of f, step 1 is we write y equals f of x. Well, f of x is x cubed plus 1. So we write y equals x cubed plus 1. The point is we write an equation where we have the formula for the function on one side and some output, some name for the output, y over here. Now we interchange x and y in the equation, and now we're going to solve the equation for y. So let's do that. So we know that x is equal to y cubed plus 1. We want to solve for y. So we're going to bring the 1 to the other side. So we have x minus 1 is equal to y cubed. Now we can take the cubed root of both sides. So the cubed root of both sides, and then we simplify that to this. So we solve for y. Y is equal to the cubed root of x minus 1. Thus, the inverse of f of x, f inverse of x, is equal to the cubed root of x minus 1. Now let's verify it. We don't really need to verify it, but let's just do it. So to verify that we have really found the inverse of f, let's see what happens if we do f inverse of f of x. Well, that's f inverse of x cubed plus 1. And now we have to do f inverse of this. So f inverse says take the input and take the cubed root, take the input, subtract 1 from it, and then take the cubed root of that. So we're going to take the input, this, we're going to subtract 1 from it, and then do the cubed root. So that gives us the cubed root of x cubed plus 1 minus 1. So that simplifies to the cubed root of x cubed, which is x. So so we see that f inverse of f of x is equal to x. Let's do another example. This is a more complicated one, as you'll see. So consider the bijective function g from z cross z to z cross c, defined by g of m comma n is equal to m plus n comma m plus 2n. We've met this function before. It's a function where the input is a pair of numbers and the output is a pair of numbers, pair of integers specifically. All right, so we would like to find the inverse of g. So step 1, now usually we would write y equals whatever, but here we don't have, the output is not a singular number. The output is a pair. So we're going to write it like this. We have the pair y comma z is equal to g of x, or g of m comma n, which is m plus n comma m plus 2n. Now we swap the inputs with the outputs. So in other words, we have m comma n is equal to y plus z comma y plus 2z. Now we want to solve for y comma z. Okay, so let's solve this. So first of all, we know, so there's going to be a lot of equations, a lot of work going on here. But let's start with what we know. So we know that y plus z is equal to m. Right? We see here we have m, and that has to equal y plus z, because if this pair is equal to this pair, that means the corresponding items in the pairs are equal to each other. So m is equal to y plus z. And y plus 2z is equal to n, right? So we have n has to be equal to y plus 2z. Now, so let's say we do this, y plus 2z minus y plus z. So y plus 2z is n, and y plus z is m. So we have n minus m. Now, if we remove the parentheses here, we have y plus 2z minus y minus z is equal to n minus m. And if we simplify that, that gives us just z, right? So that's why we did this thing here, because that allows us to isolate z, right? So we have y and minus y cancel each other out. We have positive 2z, negative z just becomes z. So we have z is equal to n minus m. So we found z. We still need to find y. So we know y plus z is equal to m, right? We have that from before. But we know z is now n minus m. So we can write this as y plus n minus m is equal to m. And now we can solve for y. So to solve for y, we will subtract n and add m. So we have m minus n plus m. And that just, I'm sorry, this is a mistake. All right, so this is 2m minus n. All right, so we have z and we have y. Thus, the pair y comma z, which is what we really want to solve for, right? Normally we want to just solve for y, but here the output consists of a pair, so we want to solve for y comma z. So y comma z is equal to 2m minus n comma n minus m, right? So y is 2m minus n, z is n minus m. Thus, the inverse of g of m comma n, right? G inverse of m comma n is defined as 2m minus n comma n minus m, this pair. Let's verify that we have truly found the inverse of g, because after all, there's a lot of potential for mistakes here. So let's see, g inverse of g of m comma n. So this is g inverse of m plus n, right? This here we're just plugging in g of m comma n. So this is m plus n comma m plus 2n. Now, G inverse says do 2 times m minus n. So in other words, take the first input, multiply it by 2, and then subtract from that the second input. So we have 2 times m plus n minus the second input, m plus 2n, comma, so going back, what does G inverse say to do? Comma, n minus m, meaning take the second input, this n, right, which is m plus 2n, and subtract from that m, which is the first input. So that's, in this case, m plus n. So, right, that's this m plus n here, this first input. All right, so now we just need to simplify it. So this becomes 2m plus 2n minus m minus 2n, comma, m plus 2n minus m minus n. And if we simplify this, we just get m comma n, right? The 2m minus m becomes m. The plus 2n minus 2n cancel each other out. And then we have m minus m, they cancel each other out. And we have 2n minus n, that becomes n. So we are left with m comma n. So we see that G inverse of G of m comma n is just equal to m comma n. So now we can be certain that we have indeed found the inverse correctly. All right, that's the end of the topic of functions.